Welcome to Calculus, a beginner's perspective. I've made this presentation to help A-level students hopefully understand the geometry and reasoning behind differentiation and the first bit of integration. Differentiation simply states the gradient at any given point on the graph. We know from GCSE that we can find the gradient of a straight line by taking the change in y and dividing it by the change in x. An alternative method of finding the gradient at a particular point of a graph is by using a ruler and drawing a line tangent to that point on the graph. You would have done this before in physics GCSE. Differentiation uses these same principles, but at a much smaller scale. Could even be considered infinitely small. If you see these three graphs, they have the square lengths in different units, with them being arbitrary. The first graph has square length 1, whilst the second one has square length 0.1, and the third has a square length of 0.01. The more we zoom in, the straighter the line gets, and so the more it resembles a linear line, which means we could use change in y over change in x to find the gradient of that line. We can use this reasoning and this graph to determine that getting the gradient from 2 points on a line is more accurate the closer those 2 points on the line are. As we can see on the graph, on the first graph with square length 1, the gradient is not very accurate to the line itself. But if we zoom in to 0.01, we see that it is a lot more accurate to the line itself and therefore the gradient. Differentiation uses the same idea, but the distance between the points is infinitely small. This gives us the most accurate gradient at that point on the line. We will be using this new notation for finding the gradient, which changes change in y over change in x into f of x plus h take away f of x over x plus h take away x, which simplifies to f of x plus h take away f of x all over h. You can also see that the function inside of another simply shows f of g of x. For differentiation, we have to use this new notation, which says that the limit of h goes to 0. This is the smallest possible value h can reach. We add that onto the original equation to get the derivative at any given point, which will give us the gradient. We will use this on a real example when the function is x cubed plus 2x. If we have x plus h all to the power 3 plus 2 times brackets x plus h, take away x cubed, take away 2x all over h, we can expand it into x cubed plus 3x squared h plus 3xh2 plus h cubed plus 2x plus 2h plus x, take away x cubed, take away 2x all over h. This simplifies into 3x squared h plus 3x h squared h cubed and 2h all over h. This simplifies into 3x squared plus 3xh plus h squared plus 2. And setting the limit h to 0 on the equation will give us 3x squared plus 2. And that is the derivative of this function at any point. This can be represented by f prime of x, or df of x over dx, or d over dx multiplied by f of x. They all mean the same thing, so it doesn't matter that much which one you use. Now we will look at some common rules you need to know in order to differentiate completely. The first one is the power rule. Derivative of x to the power of n, you must multiply it by n and subtract 1 from n in its power. If we use this method on the same function from earlier, we still get the same answer of 3x squared plus 2. The constant rule states that regardless of where a constant is in the derivative, the value given will be the same. We can see this with the constant of 3 and the function x cubed plus 2x. This gives the original derivative from earlier, but then multiplied by 3, which gives 9x squared plus 6. We can also start by multiplying the brackets by 3 to get 3x cubed plus 6x, which will also give us 9x squared plus 6. This next rule is the sum rule. It states that the derivative of a sum, or one function taking away the other, is equal to two derivatives which are either adding or taking away. I believe the sum rule is pretty self-explanatory, which is why I didn't include an example. I also need to state that if there are constants within the graph equation itself, they must be removed when differentiating them.